All right, let's just jump right in. Look, if you're into the science of bioelectrochemistry, you already know the why. Today, we're going to get our hands dirty with the how. We're talking about the actual blueprint for building a high-performance microbial fuel cell that, really works. So you've tried to build an MFC, right? You've been super patient, you've followed all the steps, but that multimeter, it's just not giving you the numbers you were dreaming of. If you've ever felt that sinking frustration of a system that just kind of underwhelms, then you know exactly what I'm talking about. And here's the thing you have to understand. The problem probably isn't the bacteria or the science itself. It's the architecture. It's all about the blueprint you're using. And the good news? That's something we can totally fix right here, right now.
You know, every great build starts with one big foundational choice. For an MFC, that choice is the chamber design. If you get this right, you're on the fast track to success. But if you get it wrong, well, you're basically building in failure from the very start.
Okay, so first up, we've got the classic design you see in a ton of research papers, the dual-chamber MFC. Its big claim to fame is this thing called a proton exchange membrane, or PEM, which neatly separates the two sides. This gives researchers amazing control, which is awesome for lab experiments, but, and this is a big but, it comes with some serious downsides for performance.
And then you've got the Challenger, the single-chamber MFC. I love this design. It's just brilliantly simple. The anode sits in the fuel, and the cathode is just open to the air, which gives it a practically endless supply of oxygen. And the best part, no expensive, fussy membrane to deal with at all.
And when you lay it all out like this, the choice becomes crystal clear, doesn't it? The dual chamber is pricey, mainly because of that special Nafion membrane, and it's a pain to build. But the real killer is that the membrane adds a ton of internal resistance, which just tanks your power output. Now the single chamber? It's cheap, it's super DIY friendly, and with no membrane, the resistance is way lower, which means the power is way higher.
And hey, you don't have to take my word for it. As the research from Logan pointed out way back in 2009, the single-chamber design just flat out dominates for anyone who actually cares about performance and building something practical. It creates a much more direct highway for electrons and protons, and that right there is the secret sauce for boosting your power density. So for our blueprint, the choice is obvious.
All right, so we've picked our chassis, the single-chamber MFC. Fantastic. Now let's pop the hood and fine-tune this thing. We're about to get into the nitty-gritty, the specific measurements that separate a pretty good design from a truly awesome one.
Now this might sound like a trick question, but I promise you it's not. There's a really simple design choice you can make that can literally double your MFC's performance. This is probably one of the most important numbers in our entire blueprint. Ready? And there it is, 2 centimeters. That is the magic number, the optimal distance to put between your anode and your cathode. So, why 2 centimeters? It's all about cutting down on what scientists call internal resistance. Think of it like this. The closer the electrodes, the shorter the commute for the protons, and the less energy gets wasted on the journey.
And this chart just shows you the insane impact. Just look at that difference. Some really great research showed that going from a 5-centimeter spacing all the way down to just 2 centimeters can boost your voltage from 0.3 volts up to 0.6. You literally double your power just by nudging 2 pieces a little closer together. I mean, that is the power of smart design.
Okay, next up, volume. For most builds you're going to do at home or in a small lab, you want to be in the sweet spot, somewhere between 100 and 500 milliliters. This range gives you a really nice balance. It's enough fuel and space for the bacteria, but not so huge that your power density starts to drop. And if you really want to max out that density, the data shows that aiming for that 200 to 300 milliliter range is the way to go.
So, we have our design, we have our dimensions. Now, what are we going to build this thing out of? See, choosing the right materials is every bit as important as the blueprint itself. You need parts that are tough, conductive, and of course, friendly to our little microbe friends.
Yeah, getting the materials right is absolutely key. Let's break it down real quick. For the chamber, you want something sturdy and non-reactive, like acrylic. For the anode, that's the home for your bacteria, you need a carbon-based material like felt or cloth, something a biofilm can really grab onto. The cathode needs a catalyst so it can efficiently snatch oxygen from the air. And hey, if you're really looking to push the limits, you can look into advanced materials like graphene to boost performance even more.
So, let's recap. We've walked through the whole blueprint: single-chamber design, tight electrode spacing, the right volume, and the best materials. But why does any of this matter? Well, let's talk about the real-world payoff.
First off, the money. By ditching that super expensive membrane and just simplifying the whole construction, our single-chamber blueprint is about 50% cheaper to build than a traditional dual-chamber cell. That makes this technology way more accessible for everyone.
And here it is. This is the real kicker. It's not just cheaper, it's so much more powerful. By cutting that internal resistance and optimizing the whole layout, this design can deliver 2 to 3 times more power than its dual-chamber cousin. You're getting way more bang for half the buck. It's an incredible win-win.
Whew, we've covered a lot of ground, so let's boil all of this down into one final, super clear, actionable blueprint. Think of these as the golden rules for building a high-performance microbial fuel cell.
Okay, here it is. Number 1, always go with the single-chamber air cathode design. 2, lock in that electrode spacing at about 2 centimeters. 3, aim for a chamber volume somewhere between 100 and 500 milliliters. 4, use carbon-based materials for your electrodes to give that biofilm a happy home. And finally, and this is a big one, remember to design for stability. Just keep the environment happy for the microbes, right? That means a pH around 7 and a nice warm temperature between 25 and 35 degrees Celsius.
So there you have it, a complete data-backed blueprint for designing and building an MFC that actually kicks butt. The science is solid, and now your engineering can be too. The only real question left is, what are you going to build?